So welcome back, Physics 221. This is Chapter 41, Atomic Physics. We will not do the entire chapter. As you can see, all we're going to do is interpret the quantum mechanical solution of the hydrogen atom and understand the basis for the shell model of the atom. So let's start. Hydrogen atom. Oops. Sorry. Come on. Hydrogen atom, the simplest element there is. Proton, that's the only particle in a nucleus, and a single electron. Now, as we discussed previously, in order to determine the energy levels, the wave functions, you have to know the potential energy function. And then you use that to solve the Schrodinger equation. So we're going to do it. So there's a Schrodinger equation again, the baby version. And the hydrogen atom is a three-dimensional object, so we really have to go 3 dimensions. And it's really a partial derivatives. If you haven't seen partial derivatives, don't worry about it. So there it is. And this is represented by that, del squared. If you haven't seen that, don't worry about it. All right, so in Physics 220, we learned that this is the potential energy between a proton and an electron in a bound state. So all we have to do is put this in here and solve it. That's all. Now, I think I mentioned this previously. The hydrogen atom is a spherical object, so you'd be insane to solve the Schrodinger equation with x, y, z. You'd really want to do it with spherical coordinates. So if you do that, here you go, right? So the spherical coordinates are theta and phi. And there it is. Isn't that awful? So we're not going to solve that. However, we are going to look at the results. Now, what's the deal with this? Okay. So what you do, so there's 3 spherical coordinates, r, theta, and phi. So you split this into 3 differential equations, 1 for each coordinate, r, theta, and phi. And then you apply the boundary conditions, as always. And when you do that, you get 3 quantum numbers that come out of it, n, l, and m. Sometimes people call this m sub l, but I guess Randy Knight calls it m. So let's talk about these 3 quantum numbers. The first one is called the principal quantum number, n. So it has to do with energy. So the energy of every state, where the state is n, right, 1, 2, 3, 4, and so forth, and so on. The energy of every quantum state is minus 13.6 electron volts over n squared. So the energy for the first, or the lowest, right, is just n equals 1, so it's just minus 13.6 electron volts. And we saw that when we talked about the Bohr atom. So that's nothing new. All right, so this is, again, but what's important is that this comes out of the solution to the Schrodinger equation, which is kind of cool. The second quantum number is L, and that has to do with angular momentum. So here's the angular momentum. This is just magnitude, right? So the magnitude of the angular momentum, and here it is. It's h bar square root L parentheses L plus 1 parentheses. And it starts at 0, and it goes to n minus 1. So that's called the orbital quantum number L. And you'll see why it's orbital later on. Okay, so that means that angular momentum is quantized, and we've seen that before. The third quantum number has to do with the z component of the angular momentum. So Lz equals mh bar. Now careful, so m goes from negative L to positive L in steps of 1. So negative L plus 1, blah, 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 0, blah, 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 L minus 1 up to L. So that's called the magnetic quantum number m. All right. So here we go, right? Energy is quantized. The magnitude of angular momentum is quantized. The direction of angular momentum is quantized. Okay? Now, for every element except for hydrogen, the energy actually depends on N and L. Hydrogen only depends on N. Okay. So people came up with this notation, and this is like ancient, before they really knew quantum mechanics, but for whatever reason it's stuck. So symbols used to represent the quantum number L. So if L is 0, it's called the S. Okay, it's the S state. If L is 1, it's the P. If L is 2, D. If L is 3, it's F. So you've probably had this in chemistry. So you just got to remember that SPDF, SPDF, just walk around campus, SPDF, SPDF, right? Sure. All right. So let's kind of do an example. Let's consider the hydrogen atom. So this is it. So again, there's the ground state, minus 13.6. The next one is minus 13.6 divided by 2 squared, which is minus 3.4. And again, you see that the energy only depends on the principal quantum number n, right? There's no splitting or anything like that. Okay. And you can see the L0 is the S, L1, P, L2, D, L3, F. Okay, so let's do it. All right, so let's say we're considering the 3D state. So what is N, the principal quantum number, and what is L? Well, this is always the principal quantum number. So N is 3. Okay, N is 3. And hopefully you recall that I said L, the maximum L is N minus 1. So for this one, N is 3, and N minus 1 is 2, so L equals 2. And I mean, that's one way to figure it out, or you can just memorize it, right? L equals 0 is S, L equals 1 is P, L equals 2 is D. I mean, however you want to figure it out. Okay, so N is 3, L is 2. So what are the N and L quantum numbers for the 5P? Okay, so let's do the 5P. So 5, that's the N, and P, you just got to memorize it. P is 1, right? So P implies L equals 1. Okay. Ah, you weren't supposed to see that. Oh, no, that's okay. All right. What's the label for an electron in this quantum state? So when you write it like that, it's always the principal quantum number first, angular momentum, and then the magnetic quantum number, M. And again, some people call it, I was always taught to say it's M sub L, but this book they just say M. Okay, whatever. Okay, so let's see. So N is 3, right? N equals 3. And what's the label for L equals 1? It's P, right? S, P, D, F. So it's P. So L is the P. And then M sub L. Now remember, M sub L goes from negative L, right? M sub L goes from negative L up to positive L. So what do you want to say? Right? Okay, so it's a 3P state. Okay, it's a 3P state. That's all you really have to say, because all we asked for is the NL. So this didn't really matter, right? But I mean, it's still okay just to realize it's possible, right? Because M sub L goes from -1 to +1. Okay, let's do the next one. So N is 4. So N is 4. Okay, L is 3. So that's F, right? So that's F. So L equals 4, which is F. And again, Oh, yeah, we don't care. So we could just write that as 4F, right? 4F. All right. Now the question, is 3F possible? So 3F means n equals 3. So that means that L, 0, 1, 2, blah, blah, blah. Now wait a second. L goes to n minus 1. Well, n minus 1 is 2, so that means the only possibilities for L are 0, 1, 2. Well, 0 is S, 1 is P, 2 is D, 3 is F, right? But 3 is not possible, right? Because the maximum L is 2, so you can't have a 3F, impossible. Okay, so you can't. L max is 2, but F means 3, so you can't do it. All right, very exciting. Okay, now this is just what I already said, but let's concentrate on this angular momentum, right? Let's concentrate on that. Now, again, I just want to emphasize, in classical mechanics, you don't quantize angular momentum. You don't quantize the direction and the magnitude, but here you do, right? Here, the magnitude and the direction are quantized. I mean, that's quantum mechanics, right? It's kind of weird. This is classical mechanics. Oh, I want to say one more. I forgot one more thing, sorry. Now notice, L equals 0 is a possibility. And if L were 0, then you'd have 0 plus 1, which is 1, times 0, which would be 0, right? So you could have L equals 0, right? You could have L equals 0. But what does it mean? What does it mean if L equals 0? I mean, if L is 0, the thing's not moving, right? I mean, right? But yet, in quantum mechanics, you can have an electron with L equals 0. So that's again, it shows you how strange quantum mechanics is. Yeah. Okay? So you can have an electron orbiting a proton in quantum mechanics with L equals 0. That is a possible state, and it's perfectly fine. All righty. Let's keep getting some practice here. All right, this is just what I wrote already. Okay, L equals 2. Let's just do L equals 2, okay? So if L equals 2, what's the magnitude? Well, then you just use this formula, right? So let's do that. So L equals h bar square root L plus 1. So that's h bar. L is 2. 2 times 3 is 6. So that's the answer. Okay, what is the z component? Wow, look. Here, this m goes from minus L to positive L. So we have 2, right? So m, it goes from L minus L, so it could be minus 2, minus 1, 0, 1, 2, right? Because it goes from minus L to positive L. So, wow, 5 different possibilities. Okay. Now, remember, hold on a second. This is the z component, right? Which has to do with direction. So there's 5 possibilities. So, all right. If m equals 2, okay, L lies somewhere on the surface of this cone. So okay, let's look at this. So here, m equals 2, right? Or positive 2. So here, if m equals 2 right here, that means that here's z, right? So it just circles. I mean, it just kind of goes like this, right? And so it's stuck. It orbits it's, here, this vector is stationary here. I mean, it's here, but this part goes like that. Okay? So if n is 2, L lies somewhere on the surface of the cone with Lz equal to 2h bar. Okay? And there it is, right? So there's L, and there's, because you can see, right? Here's Lz is 2h bar, right? We don't care. I mean, all we care about is the z component, right? The z component is 2h bar. I don't care about the angle or anything like that. That's why I can go anywhere. It can go like this. As long as that z component is 2h bar, there it is. So look at m equals 1. Now the z component is h, so it can really, right? It can go like this, right? As long as the as long as the z component is h bar. Now here the z component is 0, so what does that mean? I mean, remember, the magnitude of this thing is h bar square root of 6, right? So this magnitude is the same as that, same as that, same as that, same as that. But this has no z component, so it just goes like this, Ugh. Okay? Then here, the -1, here the -2. That's all there is to it. Okay? So 5 different possibilities. Okay, keep going. Oh, not yet. Oh, yeah. And yeah, one other thing. So this is the magnitude, right? And so basically what we have L squared equals Lx squared plus Ly squared plus Lz squared, right? So, I mean, this is quantized, this is quantized. So these two can be anything as long as this equation is held, right? As long as that equation is true. All right, very exciting. Now let's go back to what we learned last chapter and the chapter before. Let's talk about wave functions and probabilities. So this is what we had when we did one-dimensional quantum mechanics. But now we're doing the hydrogen atom, right? The hydrogen atom is not one-dimensional, it's 3 dimensions, And so we got to revise our equation. So instead of saying the probability in delta x at x, we're going to say the probability in some delta v, v is volume, at x, y, z. And probability x, y, z. And then instead of having dx, we have a dv. And then the wave function is has 3 variables, and there's a dv. That's all. So let's do it. Okay, so again, we want to use spherical coordinates, and if you're not familiar with those, don't worry about it. We're not going to actually calculate anything. So the probability in delta v at r theta phi, probability r theta phi dv, the psi r theta phi dv squared. Okay, here's the probability. Well, the probability density, sorry. So these are the graphs of the probability density. So look at that. So here's the 1s, the 2s, the 2p, and the 2p. But this is m equals 0, this is m equals plus minus 1. What do you notice? All right, so where the density, where it's darkest, that's where the highest probability density is. So here, look. An electron in the 1s state is most likely to be found at the origin. Okay. An electron in the 2s state is likely to be found either at the origin or in the surrounding shell. Remember, 3 dimensions, right? So this is a shell. The p electrons are more likely to be found in some directions than in others. So 2p with the m equals 0 here, and then this kind of looks like a donut, huh? All right. So what do you notice? I mean, you notice shell structure, right? You notice shell structure. Okay. Now, but wait a second. Let's go back to the Bohr atom. The Bohr atom, you remember, we calculated radii, right? Each quantum state, each n, had a specific, unique radius. Well, does that look like a unique, specific radius? No way, right? I mean, it's more probable here than here, but it could be here, right? Well, where is it? Well, I don't know. All I can calculate is probabilities, right? That's all you can do in quantum mechanics is calculate probabilities. So that, well, I mentioned that when we talked about the Bohr atom. You know, the whole radius thing is just wrong. Okay, so let's see. Here we go. In the Bohr model, electrons lie in distinct orbits around the proton, with the length of each orbit fixed by the need for it to comprise an integer number of de Broglie wavelengths. However, in the quantum mechanical model, the behavior of the electrons is defined entirely by the wave functions. The idea of an electron orbiting the central proton is essentially abandoned. The electron does not follow a well-defined trajectory. Instead, one can only talk about the probability of finding the electron inside a given volume V. So there it is. Welcome to quantum mechanics. All right. Now, let's just say we want to calculate the probability of finding the electron at a certain value of r. All right. So we're talking about just the radial wave functions and the radial probabilities. In other words, all we want to do is we just want to know how the probability as a function of the distance from the nucleus. We don't care, you know, the angles. All we care about is the radius. So all we care about is this guy, right? We want to know the probability as a function of r. We'll let these guys vary. We don't care, all right? We just let them vary. All right, again, don't worry about the math. I don't expect you to know how to do the math, but this is the equation you have to solve. All right, that's just the radial equation. And come on. Here are the wave functions. Okay, now they don't use psi because this is the radial wave function. So, all right, so that's why they put uppercase R. Okay. So this is the radial wave function for the 1s state, 2s state, 2p state. Now, what do you notice? I mean, don't memorize these or anything like that, but what do you notice? You notice this part, right? And what does that imply? I mean, we've seen that before. What does that imply? Tunneling, right? Tunneling, okay? So that's kind of interesting, right? Tunneling. Oh, by the way, forget it. I don't want to say that. Nothing. And also, if you look back in the previous chapter, we did the harmonic oscillator. Very similar, okay? Very, very similar. And also, one other thing, what's this? That's the Bohr radius, right? The Bohr radius. Isn't that amazing? Okay. Now, we want to calculate probabilities, just the radial probabilities. So we got to use this equation, you know, that we learned a while ago, all right? But we have to modify it a little bit because, again, all we care about, we're letting the two angular variables vary, but we want to know what the probability is as a function of r, okay? So here we go. So the question is, what is this? What's dV? Okay, so hopefully this will help. All right, so what we're saying, we want to know the probability at one particular value of r, okay? But the angles can go all over the place, right? And so what is dV? I mean, it's not the volume of a sphere, it's the volume of the shell, right, at one particular value of r. So what is the volume of a shell? Okay, so here we go. So this is r. We can say the thickness of the shell is delta r. So what's the cross-sectional, what is the surface area for a sphere? So the surface area for a sphere is 4 pi r squared. All right, so surface area surface area is 4 pi r squared. But we got to get a volume, yeah? It's a dV. So I want to know the volume of this shell, you know? So we got to multiply it by what? By the thickness. So if you multiply a surface area times a thickness, you get a volume, right? Or just write 4 pi. Right? Because there's, you know, there's a meter squared there. There's a meter there. So you get meters cubed. It's a volume. Yay! All right? That's all there is to it. So the dV for the spherical shell is just 4 pi r squared dr. So all I'm saying is if you want to just get a radial probability, that's what the dV is. So if you have a homework problem where you calculate a radial probability, you got to make sure you put in the 4 pi r squared delta r, or you won't get anything to work. Yeah. Okay, so here are some radial probability density graphs. Right? Remember, PR is the probability density. So here's the probability density at various radii. Oh, look at that. They're all in terms of the Bohr radius. Woohoo! Okay? So stare at those for a minute. And let's see if we can make some sense out of it. All right. By the way, I mean, what do you notice right off the bat? Shell structure, right? You know, here's a shell. Then here's a shell with the green 2p, and here's another shell with a yellow 2s or brown, whatever it is. Okay, you see, there's a shell structure, right? Good old shell structure. All right, what we want to do now is we want to figure out, let's make a table. In terms of the Bohr radius, let's make a table for where's the maximum probability density, okay? So let's just do that. So we have an n, and we'll have a peak, that's an r. All right, so basically we want to know where is the maximum probability for the electron to be, at what radius, okay? So let's start with a 1s. So n is 1, right? Because 1s. And where is the peak? Where would you think? Well, 1, 2, 3, probably like right here, right? And so that's like at 1 Bohr radius. So that's it. So A sub B. All right, so that's where the maximum probability is. Okay, then let's go for the 2p. So n is 2. Okay. Now, where do you think it is? It's not 5. It's probably like 4, huh? You know, again, 1, 2, 3, 4. Yeah, 4. So it's 4AB. And let's go 3D. All right, 3D. Oh, golly. Where do you think it is? It's not quite at 10. It's probably like 9, huh? Probably 9. 9 AB. Now, do you see a pattern? Look at that. You see a pattern? I hope so. What's the pattern? The peak, or the R with maximum probability, that's what I mean by R peak, okay, equals n squared times the Bohr radius, right? N equals 1, n squared is 1, n equals 2, 2 squared is 4, n equals 3, 3 squared is 9. All right, now, where have we seen something like this before? The Bohr model, right? The Bohr model. Whoa, how did he get it? Well, all right, so let's kind of think about this. So L is h bar square root of L plus 1, right? Now, this is always going to be max, is a max when L equals n minus 1, right? Remember L goes from, yeah. L is 0, 1, 2, blah, 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 n minus 1, right? So the maximum L is just n minus 1, right? Okay, so that makes sense. So where do you have your maximum angular momentum? So this is the physics, I don't know, 121 question, I guess. I already showed you that. Okay, so this is physics 121. Where do you have your maximum angular momentum? You have your maximum angular momentum with a circle. You don't have it with an ellipse. Here, let's read this thing. The circular orbit has the largest angular momentum, physics 121. The electron stays at a constant distance from the nucleus. The elliptical orbit has a smaller angular momentum. Compared to the circular orbit, the electron gets both closer to and farther from the nucleus. Both orbits have the same total energy, E. Okay? So all I'm saying is that when Bohr figured out his model of the atom, what kind of orbits did he have? Circular orbits, right? So circular orbits correspond to maximum L, right? And what we looked at the maximum L, right? For n, the maximum L, well, let me go back to the slide. All right, so for n equals 1, the maximum L is a S. For n equals 2, the maximum L is a P, right? For n equals 3, the maximum L is a D. So all we were looking at when we were looking at this thing, we were looking at the maximum L's, which correspond to circular orbits, and we came up with this equation. Well, the reason we came up with this equation is because we were kind of looking at the maximum L. Maximum L corresponds to circular orbits. That's what Bohr did. So it makes sense. Okay, we're probably too long. Let's quit.